All right, so I'm going to do problems 1015 and 1027. 1015 basically asked us to look at an example from earlier in the chapter, example 10.9, where it calculated the partial pressure of toluene given certain conditions. And the question we were given is to, because the example just takes that pressure and then tells us that the temperature for that partial pressure is -60, and it just asked us to do the calculations to find that temperature. So basically, we took the pressure it gave us. Partial pressure was 5 pascals. Convert that to millimeters of Hg, which is what's necessary for the Antoine equation. So, yeah, this is the Antoine equation, and these are the constants from the back of the book for toluene. And you just have to rearrange Antoine's equation algebraically so that you can get temperature, plug everything in, and you get -60 degrees Celsius. This sort of problem is important because oftentimes you do know what pressure you're operating at, and you want to know what temperature gives you the partial pressure for that specific compound. Yeah. Any questions? Pretty straightforward. Problem 1027 was the problem that asked us. It was about a painter's face mask. Had 2 small charcoal canisters, and it gave us, these were the constants for the, what was it? He was breathing toluene, and these were the constants, and this is the formula from the book that you get for plugging into the chart. Figure 1011. Anyway, you plug those values in and you get 3.64, which on page 357 on the chart corresponds to a value of, I got 37 on the weight absorbed per weight adsorbent. And it gives you a formula there too. It's where is it? Well, anyway, it's around there. And you plug that in, plug in 37, and you get 0.289 pounds toluene per pound sorbent. And you can convert that to grams, toluene per gram sorbent, and there's 100 grams of charcoal sorbent in the 2 canisters combined. So you multiply that through, and you get 28.9 grams of toluene for the 2 canisters is its capacity, basically. So we know that, and now we need to calculate how much toluene he will breathe, or how long it will take him to breathe 28.9 grams of toluene. And this is our concentration in ppms, 1,000 parts per million. Multiply that by, he breathes, it said 15 kilograms of air every 24 hours. So 15,000 grams of air, and then you have to convert that to moles of air because ppms isn't mass, it's molar. So then you get 0.5172 moles per 24 hours of air, or of toluene. Convert that back into grams of toluene. Here, we've got 47.58 grams of toluene breathed every 24 hours. So then basically you take this and divide it by that, you get your units, and you get a total of, it takes them 14.6 hours to use up the canisters, basically. This would be important because, yeah, it's the sort of calculation you'd want to use to calculate how long it takes to basically use up any sort of filter like that. Right? Any questions? Comments? Criticisms?
Is that a conservative estimate, or would you want to rely on that if you were the painter?
Well, I'd probably realistically include a factor of safety and probably say it would be spent after 11 hours or something, whatever your factor of safety would be. That's probably getting dangerous because...
What's the assumption that you've made here, that the book told you to make as far as the breakthrough curve?
Well, I don't recall exactly what the book said. I'd have to read it, but I think that what it says is basically, because what would really happen is as the filter starts getting saturated with the toluene, that there would begin to be sort of an increase in the level of toluene coming out the other side of the filter. But this kind of assumes that it's just a sudden breakthrough point rather than a gradual.
Yeah, so this is called the ideal breakthrough curve.
Right. So it looks like that rather than
Exactly.
that.
Yeah.
So yeah, you'd really want to say that would be the
Precisely. Yeah.
breakoff point.
Thanks, Jake.
Yep.
Any other questions? Are you all done? Lisa?
I'll turn it over to Jake for the theory.
All right. So this is a diagram. I'm going to go this way of the.
Sorry.
You smacked him, tripping over stuff. This is a picture of the U-tube heat exchanger. Yeah, obviously, the shell side fluid goes in. There's baffles that get circulated through. Heat transfers with the tubes, and fluid goes out. So what do I do? Push enter. Okay. Yeah. So these are the specs of the heat exchanger. Okay. So these are the equations that that we used to find the actual U. We used this equation. Wait. What do we do? Yeah. We use this equation. Well, we calculated U using this. We calculated Q using this equation here. And then we were able to plug it into this equation and solve for U. And that's what we got for our actual U. For our experimental, and for our theoretical, we use this equation here. And we got these from using the Nusselt numbers and all that stuff. This was our actual data. Wait, am I done? Or am I supposed to? Okay. This is our actual data. Pretty good looking chart there. And I'm turning it over to Jeff now.
All right, so these are the results we got for our experimental values.
Can you have any questions?
Yeah, we got it that It's a result from copy and paste.
I have one question. Shouldn't the diagram you have the heat exchanger